In this video, I'm going to give a very brief introduction to leptons. Leptons are some of the fermions in the standard model. So they're spin 1/2, and they do not like to be in the same state as each other. So the leptons are the fermions which do not have any interaction with the strong force. So they don't have any color, is what we would say. So they don't interact with gluons, and that's one of our ways we can distinguish leptons from quarks, which are our other fermions. And so we see over here, these are our 6 leptons. So the electron, which is probably the most familiar particle to you, it is a lepton. And we have one of the ways we categorize our leptons is into generations. And so here we have our first generation of leptons, which is the electron and its associated neutrino, which we refer to as the electron neutrino. Our second generation has a muon and a muon neutrino. Now, a muon is often described as a heavy electron because you'll notice the muon has all of the same properties as the electron, except it is more massive, which is to say it also has charge -1, and it also is spin 1/2. So it's very similar to the electron in all ways, except for the fact that it is more massive. So that means that muons are going to they're going to be unstable particles, and they're going to tend to want to decay to become electrons. So part of why we see a lot of electrons in nature, and you probably never learned about muons even in high school chemistry or wherever you first learned about electrons, you probably didn't learn about muons. And that's partly because they have very short lifetimes, because they're unstable particles. The way we understand nature is that more massive particles are always going to want to decay to be lighter particles, unless if there's some reason that they cannot. So the muon, the fact that it's very similar to the electron, just more massive, means that it's always going to tend to want to decay to be an electron. So it has a short lifetime and tends to want to decay. And also I should say, excuse me, in that second generation, we also have the muon neutrino, which is a neutrino associated with our muon. In our third generation, we have our tau particle and our associated tau neutrino. You'll notice the tau is even more massive than the muon. Again, when we organize our generations, each generation gets more massive. So the tau is going to have an even shorter lifetime than our muon. It's going to decay very fast. So it actually took us a long time to discover the tau particle. So our leptons are made up of, the electron, the muon, and the tau, and then these 3 neutrinos which are associated with them. So if we now sort of focus back on our neutrinos on the lower row, neutrinos are neutral. That's why they're called neutrinos. And then the ino ending, right, suggests that they're small. So neutrinos are very, very light particles. And for a time, scientists actually wondered whether they were massless because their mass was so tiny. Then people thought maybe they were massless. We now know that they do have mass. They must have some mass. We actually don't know exactly what that value is. And instead, we have only an upper limit on that value. And you'll notice the units are different. So if we look at the electron neutrino, it's in electron volts, right? As opposed to the electron is in mega electron volts, right? So these are a lot smaller than their counterparts, right? So the muon neutrino is much lighter. It does have MeV units, but 0.17. As opposed to the 105 mega electron volt muon. So neutrinos are very tiny particles, which are neutral. And there's one associated with each of our electrons. And one of the reasons we give our neutrinos these names, and part of also why we group them into generations in the way that we do, it's not just randomly because of the mass. So we'll learn that the weak force is going to allow electrons to interact with electron neutrinos. And we'll see that there are conservation properties associated with sort of electronness. So if we start with an electron and it's going to decay into something else, we sort of conserve electronness in that we have an electron neutrino that might come out, or we might have an electron and an anti-electron neutrino that are interacting with each other. And so these generations are also going to govern the way particles are going to interact with each other under actually the weak force in particular, in the case that I'm talking about. If you didn't understand anything of what I just said, that's really fine, because we'll dive deeper into that in the future. But I thought it was at least worth mentioning that these names are not random. We're going to see that the way an electron neutrino interacts with an electron is very different than how a muon neutrino would interact with an electron, because there are conservation principles that allow certain things to happen and certain other things to not happen. Okay, so that's the basic properties of our leptons. Those are our, well, again, we have these 6 leptons, but then we also have all of the anti-leptons that